Thank you very much. So what I want to do now is to look at what can we actually do with orbits for bigger cases. Yeah? Imagine you have a group of order 10 to the 20 or so. You have absolutely no chance to write out all elements. I mean, you could use, for a smaller group, you can use the orbit algorithm to enumerate all elements of the group, but you can't do this in general. So this was, yeah, I wasn't sure that they were edge to edge. That's why there is a brief repetition of what we've just seen. We can calculate the orbit of a point, stabilizer of a point, transporter elements, as long as the orbit fits into memory. We can calculate the permutation image of a group if a group acts on itself by right multiplication. We get the list of elements of the group. That way we could calculate the order of a group. We could test whether an element is in the group as long as it is not too big. If we take the action on its elements or its subgroups by conjugation, stabilizers or centralizers or normalizers. But, well, and what we can do is, and I didn't write it out how to because it's a bit messy how to write it down, but when I get new elements in an orbit, I can keep track how they were obtained. So if a group acts on itself by right multiplication, I actually can trace through the transversal how an element was obtained as product of generators. And that's what I call constructive membership. By that I mean not just testing whether an element is in the group, but if it is in the group, to calculate, to write out how it is written as a product of generators. But if the group is larger, the regular action, the action of a group on its elements, just that will not work. So more is needed. And that leads me to some further remarks about the performance of the orbit algorithm. The memory really is the limit here. How can I save memory? For example, by not multiplying out the transversal elements, but remembering each transversal element as a product of generators and just multiplying on the fly. That is called sometimes a Schreier vector. By writing, but then the question is just to write this. You basically get a construction tree to make the depth of this tree small, so not too many elements have been to be multiplied. The cost of the algorithm actually is dominated by this element test in the orbit. If you get a point, is it new in the orbit? And that is basically a data structure issue. You want to have a data structure where you can quickly tell which represents a set, and where you can quickly set whether an element is in the set or not. And the tool GAP uses in GAP, this tool is called dictionaries. You find information about it in the manual if you're interested, or ask me. And as I mentioned by now, probably even more often than you really wanted, the total number of Schreier generators is the length of the orbit times number of the generators, or stabilizer index, times number of generators. A lot of them are trivial, many more are redundant. How can I handle this? And there are basically three tools which have been used more generally for reducing the number of generators. The first tool is that one actually, if we build a data structure which allows us to test for membership, we can use a similar data structure for the stabilizer, which is we know so far, the partial stabilizer, and discard Schreier generators if they lie in the stabilizer generated so far. That is basically the main tool in what is called the Schreier-Sims algorithm. Schreier, we know, Sims named after Charles Sims. Oops, sorry, that was too quick. Which is used for, which I will describe more on the next slides. One can, instead of using the Schreier generators, one might just want to take a random subset of them, or what turns out to work even better, take some of them, multiply them, basically taking some products of random products, but random of a particular form, called random subproducts, and use them instead. The issue, if we don't take all, is of course we don't have necessarily then a proof that it generates the stabilizer. If we know the group order, that is fine, one can do so. Otherwise, one would need to verify later, and one can do this from what is basically a composition tree, which I will also talk about later. So, let me mention first the ideas of Sims for describing a permutation group. And the ideas basically built on what is sometimes called a divide and conquer approach. And the way I want to describe it here actually is in a slightly more general way. What would be a plausible way to implement a divide and conquer approach for a group? What would be smaller things? Smaller things would be a subgroup or a subgroup and its cosets. Or if the subgroup is a normal subgroup, it would be this subgroup and the factor group. Well, the subgroup could be a stabilizer, and I can calculate stabilizers if orbit lengths are not too long. Caveat, that is not always the case. So for example, if you take SLNQ, n by n matrices over the field with q elements, and you act on the natural vector space, you basically, the only short orbit you have is the orbit of the zero vector. Otherwise, you don't have nice short orbits, because all vectors lie, all non-zero vectors lie in one orbit. Yeah, so that does not always work, or the subgroup might be the kernel of an action, and that's the tool for composition tree. And I will basically describe it as a single-step process, but very naturally one can do a multi-step process by just considering then the subgroup again in the same way. So let's first look at the case of permutation action, and the subgroup is a point stabilizer. So the basic tool there is what is called a stabilizer chain. So I choose a set of points. Well, choose actually turns out that I typically make that choice in the algorithm by adding more points if needed. But for the theoretical description, it's easier to think about it that these points are chosen. A subset of the set omega, or well, and actually it's not a set, it's a list of points. A sublist of omega is called a base if the only element in the group which maps every point to itself is the identity. And that means that I can describe every element by its unique base image. Because if two elements have the same base image, their quotient will map every base point to itself, and therefore by this condition will be the identity. So that condition exactly is equivalent to knowing the image of of all base points describes a group element uniquely. And associated to this base, I can think about a chain of stabilizers which get smaller and smaller. I start with a group. I stabilize the first point, then in there I stabilize the second point. So I stabilize the first point and the second point and the third point and the fourth point and so forth. And I get a chain of subgroups which get smaller and smaller. And if I stabilize all the points, well, then only the identity is left. Then I have the trivial subgroup. Well, I have a trivial subgroup without the closing bracket because I made a mistake there. Yeah. So I can build such a chain recursively through what I mentioned before is the Schreier-Sims algorithm. And I didn't want to write it out in detail because basically that is a ready implemented algorithm which you probably never really look at the innards but will just use as a tool. But let me briefly describe what the algorithm does. The algorithm starts with a point, with the first point beta 1, and calculates its orbit. Orbit, transversal, and stabilizer. So, whenever we get a Schreier generator for the stabilizer, well, which is not the identity, and we can test that under the assumption, so if that element doesn't fix all the base points, then we call that routine for the stabilizer recursively. So it actually is a routine whose input is that we have the existing data structure and we add a new generator. So we have already an orbit so far. We add a new generator that will expand the orbit, which one can do with a variant of the orbit algorithm. We expand the orbit, we get new Schreier generators. For those which are not trivial, we call the routine recursively. And what the routine actually also does on the start, it's called recursively for the stabilizer, which has the same kind of data structure. At the very start, the existing data structure, which describes the partial stabilizer or the group or a subgroup of the group, is used for testing membership. And I will tell you in a moment how one can do the membership using this data structure. We are testing membership in the partial group. If the element Schreier generator is in there, it is redundant. We can discard it. Otherwise, we use it to extend the orbit there and so on. And you get a recursive algorithm where all the Schreier generators are always fed down to the next level, but tested first whether they're really needed. And that reduces significantly the number of Schreier generators which one needs to use, and that makes it feasible to build this data structure. So what we get is actually, we don't just get these subgroups. In each case, we get the orbit of the ith base point under the I minus first group in the chain. And we get the corresponding transversals. So that's really what a stabilizer chain is. Yeah. Now, how can we test membership if we have such a chain? We take the element, we look at what is the image of the first base point under that element. If the image is in the orbit, in the first orbit, well, if it's not in the first orbit, we know the element cannot be in the group. So let's assume the image of the first base point is in the first orbit. I have a transversal element for that point. I divide off that transversal element and I will get something in the stabilizer. Or if the element is in the group, then this quotient is in the stabilizer. So that membership test recursively goes to the stabilizer, which is a smaller problem. And then I repeat, smaller and smaller stabilizer till I end with membership test in the trivial group, which I can do easily. I can keep track how generators were obtained and thereby basically can even write an element as a product in generators. So I get not just membership, but constructive membership. I can evaluate homomorphisms. I also get a bijection because I said two elements are the same if and only if the base images are the same. So I get a bijection between the elements of the group and the set of base images. In general, base images, so unless your group is a symmetric group, if it's a symmetric group, of course, of degree n, it has base n minus 1. But in general, if you have a group which has, I don't know, acts on 10,000 points, your base might just have 2 or 3 points. So base images takes very much less space than group elements. And one can use this instead of storing lots of group elements to just store base images. That saves memory. Or even more, one can use this to describe the group elements through base images. For example, the number of possible base images is the order of the group. And the number of possible base images is the product of the orbit lengths on all the levels. Or you use the orbit stabilizer theorem, right? The order of the group is the length of the orbit times order of the stabilizer. Order of the stabilizer you calculate recursively again in the same way. So you get the order of the group. You can use this to enumerate the elements because you can enumerate the base images. And that enumeration actually gives us a way to represent the group in the form of a tree. And I just want to give you an easy example of this by taking the alternating group on 4 points. Yeah? I'm looking at the image of the point 1 and the image of the point 2. And that gives me 4 choices here and then 3 choices each, in total 4 times 3, which is 12 choices, which is the order of the group. So if you go through this tree, basically the numbers you get are the 2 points of the base image, and that describes the elements of the group. So for example, the element 1, 3 is the element which maps the point 1 to 3 and the point 2 to 1, and indeed this is what the base images are. Yeah, 3, 1. And here near it I've written the corresponding transversal elements, how one could write these elements as a product. Okay, now I have a nice regular tree. There are nice, easy algorithms for traversing a tree. So I can write algorithms that run through all elements of the group without having to write these elements all down. And I can run through, if I want an element with a particular property, I can try to run through all elements and test whether I find an element with this property, or to find a subgroup with a particular property. And such a search is called a backtrack search. And it is used in GAP, for example, to calculate the centralizer of elements in a permutation group, to calculate the normalizer of a permutation group. Yeah?
In your example, the basis is 1, 2, 3, 4?
No, the base is 1, 2, because it's the alternating group A4 and not the symmetric group.
Okay.
Yeah?
And you only represent the generators of the group?
What I'm writing down here are the transversal elements. Yeah? So I didn't write down what the generators are because, well, why A? Because there wasn't space to write it down. And basically for the decomposition, you just need the transversal elements. You could take, if you want, you could take 1, 2, 3 and 2, 4, 3 or 2, 3, 4 as generators. Yeah? And then I have that base of length 2 because I have the 4 times 3, 12 elements in A4. Yeah? Thank you.
The length of the base is the height of the tree?
Yes, yes.
Or the depth?
Yes, yes. And here, if you take the symmetric group or the alternating group, you get a tree which looks in some way most regular, but very few groups are the symmetric group or the alternating group. So in some way, while the width on each level are the same, the width might be vastly different between different levels and might even increase on lower levels again or so. Up here? No, because that is just the head. I don't have a point there, yeah? There I'm not stabilizing, and that's the full group. I'm not stabilizing any point yet. Yeah, I could put the point 5 there if I say I want to consider the group acting on the points 1 to 5, yeah? So I can use standard computer science algorithms, depth first transversal, to run through all elements in the group and find elements with the right property. And that is used, yeah, centralizer, normalizer, conjugacy test for permutations, which goes through representative action, set stabilizer, which is stabilizer with on sets, intersection of subgroups. The generic functions are element property, subgroup property. So that can be used for a lot of questions in permutation groups. Of course, I'm still running through all elements. If my group has 10 to the 20 elements, by memory I can do it, by time not. So the crucial thing, and that is something, well, it's the usual bad thing, the most interesting bit people don't tell you, and I'm not telling you because that gets quickly quite messy to quite messy combinatorial problems. The crucial step for this backtrack search is to actually not run through the whole tree, but to prune branches of the tree where you know you don't need to search. And the pruning is depends on the concrete problem which is asked. So, for example, if you are looking for elements which centralize the permutation 1, 2, the two cycles of the points 1 and 2, yeah? You can ask, where is the point 1 moved? If the point 1 is moved to 2, the point 2 can only be moved to 1. Otherwise, that element will not centralize 1, 2. Yeah, then that's basically the pigeonhole principle or so. And so you can use ideas like this to then basically cut off the branches, that if you know the image of your first of 1 is, this is the image of 1, this would be the image of 2, the image of 1 is 2, that you know in that case this branch here and that branch here can be cut off. And often if you have more points, this is much deeper, and cutting off branches really reduces the search. That is what makes the backtrack search feasible. It does not help with the complexity. The complexity of backtrack search is very much exponential, is basically the worst case could be running through all elements of the group. But for all of these applications here, there has been development of a lot of such suitable pruning functions which are used to, or can be, which are used to make these calculations feasible. So that's stabilizer chain, backtrack. That's basically what happens if you have if you only have permutation groups, or only permutation groups which are not too big. But permutation groups can be bigger, and there is still the problem of the number of generators. And therefore, to resolve this actually is not to take these algorithms and just modify them a bit. The resolution of this is basically to look at it in a different, completely, well, not completely, but in a different way, basically looking at it from the other side. And that's why the next slide has a different background color. So, I said stabilizer chains, the number of generators, that is the problem. So, the solution for this is, well, something which initially seems to be rather wrong. The solution is to say, oh, if we don't require the result to be correct, we probably can give an answer easier. Yes. If I don't need to give correct answers in the exam, I will be done after 5 minutes by just writing something. But of course, we in the end want correct answers. So, the paradigm which is used is that we first don't aim very hard to have the correct result. We are trying making some choices or some selection. For example, don't take all Schreier generators, just take some of them and hope we are lucky. And one can make statistic studies of how many one needs to take that one has a good chance of being lucky. And of course, that could be a wrong data structure. Based on this potentially wrong data structure, we determine more about the structure of the group. Basically, we determine a presentation, and I will tell you in my lecture more about presentations. And then we use that information about the structure to show, well, we get information about the structure. If we've made an error, we are missing something. The structure we're describing is too small. It's not really the group we have, but we are imagining a smaller thing. And then we try to fit that structural information to the group. But what will happen if it is too small, like a t-shirt on a fat American, it will not fit, it will stretch too far, yeah? And you run into you will see that, and that will tell you that an error must have happened, or not an error happened, that you were not lucky. But if you find in the end, and I know this is a little bit vague, in the next lecture when we do presentations, I will tell you more concretely what it means. But we are in a situation where we make first some random choices to calculate a structure, possibly wrong. We use that structure to determine that data structure to determine the algebraic structure of the group. We try to make this algebraic structure fit the group as a group of permutations, say, or a group of matrices. If it does, we will have proven that we were lucky and everything worked, or it will tell us something went wrong. And if it went wrong, well, we can just start again and hope we are lucky next time. And the only thing we need for that is some indication which says, oh, if you make that many choices, you have a good chance to be lucky. And frankly, the selections which are done are typically that one has, I don't know, that your chance of being unlucky is 10 to the minus 10 or something like that. So this failure case happens very rarely or never happens in practice, but we have a verification which checks that it didn't fail. And such an algorithm that does some random things and in the end verifies that the random things indeed gave the correct result, or it says, oh, the random things, there was a mistake, start again. That is called a Las Vegas algorithm. The different name, you might have heard Monte Carlo algorithm. The different name is basically from complexity theory in that we cannot bound the runtime because we cannot guarantee that we are at most 3 times unlucky. In the very worst case, you would be unlucky. That you could be an unbounded amount of times unlucky. And so the worst case runtime of such algorithms is unbounded. But in practice, you will very rarely be unlucky. And so the practical runtime is good. And that's basically the tool which will be used to get around this issue of the large number of Schreier generators. Okay, so how do we do this concretely? Yeah, and that is, that again basically says the same. I should have skipped. Yeah, that is basically that is saying the same as the previous slide, just in a different way. So the tool for this is to calculate a composition series of a group, or actually it will have a tree structure. That's why it is called a composition tree. It's a data structure. It's a tool which is basically also which is also used for working with matrix over finite fields, or more generally finite matrix groups. One can basically describe it agnostic of how the group elements are represented. And the three gentlemen whom I'm listing there, Eamon O'Brien, Charles Leatham Green, and Derek Holt, probably are the three who have done most towards making this work for matrix groups. So it's a tool developed for matrix groups, but it's really a tool one can also use with the same ideas for permutation groups. And that's what I want to describe next. And it follows this paradigm on the blue slide. We are not immediately trying to get a correct result, but we are trying to make good guesses and in the end verify that everything went well. Okay, so how does this work? We want to find a composition series. A composition series is a series of factors of subgroups, or a composition is a series of subgroups, so that the factor, that each subsequent factor is a simple group that I can't cut it smaller again. It's a bit like atoms. Well, how can I find atoms for a structure? And that is something not just here in group theory, it's even something in chemistry or so. How do I find the smallest parts? I'm using what I call the breadcrumb algorithm. How do I construct breadcrumbs? I take a piece of bread and I break it apart. And if they are not yet crumbs, I break them apart again. And so on. Yeah? That's how you make breadcrumbs. And in general, if you apply this to something arbitrary, there is nothing which tells you that your result is unique. If you have two isomorphic pieces of bread and you give them to two people and you say make crumbs from them, it's unlikely that they even end up with the same number. But that's because we don't have nice theorems about bread. For groups, we have the Journo-Hilder theorem, which tells us regardless how you chop it apart, you end up with the same parts in the same number. And if you want, that's one of the basic paradigms of chemistry, that regardless how you take a substance apart, you always end up with the same number of the same kinds of atoms. If you didn't have this, you wouldn't have chemistry as it nowadays exists. Yeah? So, because of Journo-Hilder, we can use that algorithm. What we need to find a composition series, actually, is only two steps. We need one step which says, oh, I have a group. If it is not simple, I want to find a normal subgroup in there, or I want to find a homomorphism with a non-trivial kernel, or I want to be able to show that I have found an atom. That means I have found a group which is simple. Yeah? And here I'm using it for groups, but I mean, basically, you could use the same algorithm for chemical analysis. If you can do these two things, you have a substance, you can either say this substance consists of multiple atoms, and here are two parts which both have fewer atoms in, or you have the second step. Here is something, this is really just one atom, and I tell you which atom it is. That's what that's all of chemistry. I'm not a chemist, so I don't tell you how to do it for physical substances, but I tell you how to do this for groups. So what I want to do is, what I need is really, and let me first talk about the first part. How do I chop it apart? If my group is not simple, I need to find a homomorphism with a kernel that is smaller. And why do I want the homomorphism and not a normal subgroup? Because the image of the homomorphism also gives me the quotient, and then I have the two parts of the group. I have the factor group and the normal subgroup. So I want a homomorphism with an image that is smaller. Why do I have smaller in inverted commas? Because in practice it turns out to be useful also to have the case that the kernel is trivial, but the image is smaller in processing costs. That are stages you don't have in chemistry. Basically, you might in between want to go to isomorphic structures if it turns out that they are easier to work with. Yeah, and then we recurse to image and kernel. That's going to the two breadcrumbs we got from two parts from breaking the bread initially apart. Yeah, and so that's how we proceed this. So how do we find such homomorphisms? Well, we find homomorphisms through group actions, acting on something. It might be the natural action, the permutation action, or building on the natural action, the permutation action of permutation groups, the matrix action of matrix groups, or it might be an action on parts of the group structure. And the main tool there is two theorems, which I'm throwing together here into one, the Onen-Scott theorem and Aschbacher's theorem. Onen-Scott is a theorem about permutation groups. Aschbacher is a theorem about matrix groups over finite fields. And these theorems, they are named after Leonard Scott, Michael Onen, and Michael Aschbacher. And what these theorems do is you have a permutation group or a matrix group. Then either there exists some structure which for a permutation group is combinatorial, for a matrix group is geometric, which is stabilized by that group. And using that structure will give us an action. Easy example, if you have a permutation group which is imprimitive, then your structure is a partition of your original set into blocks. Yeah? For example, dihedral group, the 8 symmetries of a square, if you partition your 4 points in the two diagonals, the partition 1, 3 and 2, 4 is fixed under the group, and the group acts on this partition. You get a homomorphism to the symmetric group S2 that is smaller. That would be such a homomorphism. And these two theorems basically say this is always possible unless the group is almost simple. Almost simple just means simple with some automorphisms on top. Let's ignore the automorphisms for the moment. They are just a technical issue. Yeah, and that's exactly this splitting process. And what I get is I end up with such a tree structure. I start with a group, I get a homomorphism, I recurse to kernel and image, and then I do the same here. For the kernel, I get some homomorphism, which has again a kernel and an image, and so on. And what are the leaves of the tree? The leaves of the tree then basically are the, well, almost simple groups or practically are the simple groups, the simple composition factors. Yeah, so that's the idea. The question is just, how do I find such homomorphisms? Yeah, for permutation groups, if the group is intransitive, I can act on an orbit. If it is imprimitive, I can act on blocks. If it is primitive, that means there is no partition of the points, which as a partition is invariant under the group. There, the Owen and Scott theorem tells me a lot about the group structure, and I can, for example, act on components of the socle or so. And basically, one could give a whole lecture series about just how to find such homomorphisms. That is something which went under the name of matrix group recognition and has been a major research project for 10, 15 years. But I want to give you just a flavor of how to do this. For matrix groups, well, if the matrix group acts reducibly, that means I have a subgroup module. I actually have a submodule in the factor module and can look at the action on these two modules. If it's irreducible, there are these what are called the Aschbacher classes, which play similar roles as here. And yeah, for time reasons, I don't want to go into details of what these Aschbacher classes are. But what I want to do, because I think it's a useful tool, is, well, here I'm saying if the group acts reducibly, if there is a if the natural module, that means the vector space in the dimension where the group is given by matrices, has a submodule. How do I actually find a submodule? Or how can I say that there isn't a submodule? And that is a tool which is called the MeetX, and I briefly want to talk about this because it's a very useful tool for many algorithms, and I think it is not as well known as it deserves to. So what is the setup here? I'm briefly stepping away from the question of this finding a composition tree. I have a group, a field, a homomorphism from the group into a group of matrices. That is a matrix representation. That vector space over that field in that dimension is the natural module. A subspace that is preserved as a subspace, not element-wise, but just as a subspace under this action, is called a submodule. And if such a submodule exists, which is non-trivial, then this matrix representation is called reducible. If you prefer the concrete matrices over the abstract submodule language, what I'm saying is my submodule, if I choose a basis, that the first few basis vectors form a basis of the submodule, of the subspace, and then I extend it to a basis of the whole space. In that basis, the matrices all have such a block structure with a zero block here. Why is my block on the bottom left? Because I'm acting on the right. If you're acting on the left, you would typically have the zero here. Or if you expect the zero here, you are accustomed to acting on the left. Yeah, so how can I find, yeah?
S is a subvector space, or it can also be a lattice?
That would, no, a subvector, sorry. Here, this would be subvector space, yeah. No. This is basically, this is a linear algebra over a field thing. If you only go, this doesn't work for taking a subring. No, that would be nice, but yeah, that doesn't work there. Okay. Well, in this case, I mentioned already, then I get basically two constituent representations. The action on the submodule, which is this part of the block, of this block of the matrix, the action on the factor module, which is this block of the matrix. The kernels of these two homomorphisms might intersect non-trivially if the characteristic divides the group order. But yeah, let's not worry about this. But how can we find submodules? And that goes by the name of Norton's irreducibility criterion, named after Simon Norton, who came up with this. And that criterion is a theorem which basically, it's written here to describe it, write it properly as a theorem. But basically, and I might not even go through all the cases, what I'm doing is I will find an element which is a linear combination of the matrices which are in the group, which are images of the group. Or if you've done representation theory, it's the image of an element in the group algebra. And I want such an element which has a non-trivial kernel. Yeah, images of group elements never have a kernel, but images in the group algebra can have non-trivial kernel. And the criterion says the representation is irreducible if and only if every vector in the kernel of M does not span a proper submodule. If I take the submodule generated by this vector, that's the spinning algorithm I mentioned in the last lecture, this submodule is the full module, and the same for the transposed matrix. And formally, this is something in the dual module, but really one can look at it just in the matrix case. Okay. That looks somehow strange as a criterion, so let me show you the proof, because the proof is really very easy. The proof says I'm testing first whether I take certain vectors and I look at the submodules spanned by them. Well, if that submodule is a proper submodule, I found a proper submodule, the representation can't be irreducible. Done. The same with the transposed matrices and the dual module, then I find a proper submodule of the dual module. Its dual object or orthogonal object is a submodule of the original module, so again I have found a submodule. So what I just need to show is that one of these submodules I will always find. So, and that's really the core of the proof. Let's suppose the representation is reducible, and I have a submodule, and I write my matrices in a basis which represents this submodule. Why do I have to have an element in one of the two kernels which will expose that submodule? Well, and that is now essentially first linear algebra class. This matrix, it was chosen to have a non-trivial kernel. That means the determinant of this matrix is 0. That means we have the determinant of this submatrix A is 0, or the determinant of the submatrix B is 0, or both. But one of the two determinants needs to be 0. So let's assume the determinant of A is 0. Then there exists a vector which I can multiply with A, which gives me 0. And if I take that vector and I pad it with further zeros, that vector times M gives me 0. Yeah? But this padded vector has non-zero entries in the first few components, so that vector is in the span of the first few basis vectors, which is the submodule. And if the determinant of B is 0, I do the same with the transposed matrix, respectively the dual module, and I have the same situation. So that tells me, that shows me how I can find such submodules. And it's a constructive test. If the group is, the test tells me either the group acts irreducibly, there is no proper submodule, or it tells me here is a submodule, namely the submodule spanned by the vectors in the kernel. Yeah, that's the irreducibility test, and building on this, the tool is called the meetx, and indeed this is meetx is exactly what you imagine. It's this butcher's tool. It's named after this butcher's tool to cut things small, because that's what it does with a module. You take a module and you cut it apart. It's a slightly more brutal version of the breadcrumbs. This was invented by Richard Parker. This in a conference proceedings paper in '84. Yeah, and what it does is basically it finds by random search a matrix, linear combination of products of the matrix generators of the group that has low dimensional but not zero kernel. It applies this irreducibility criterion. Either it proves the module is irreducible, or it finds a proper submodule. If it is reducible, change basis, take the blocks, action on the submodule, action on the factor module, recurse, breadcrumb algorithm, and you do this as often as you need, till you find the things which can't be cut smaller. In this case, that would be the composition factors of the module. And one can generalize this, well, geometric or other module, I really should have said, for other module constructions. So one can, there are generalizations to do then to test module isomorphism and so on. Yeah. How does it work in GAP? And the one thing to mention here is just to understand why the functions look like this. When you do linear algebra, you can do two kinds of linear algebra. And you see the two kinds if you have colleagues who are very pure or very applied, and you look how do they teach linear algebra. The very pure person will teach linear algebra by talking about vector spaces, subspaces, transformation. There never will be a matrix. Worst example, take the book Linear Algebra Done Right, which is horrible because the author basically desperately tries to avoid matrices. The other extreme side, which some unnamed people teach, is that linear algebra is all about matrices. The word vector space is mentioned once or twice, and otherwise you have matrices and you do LR decomposition and QR decomposition and all these things, yeah? But of course, in some way it's the same world. Here, the concept of a basis connects these two worlds, and you need, I feel to do linear algebra correctly, you need to take both views. But for computation, of course, the matrix view is the concrete one. There is I think it's Halmor-Schlin, I don't know whether it's his linear algebra book or whether he was just cited on it, where he says, yes, when we talk abstractly about vector spaces, we talk about these sets and axioms, but as soon as a problem becomes concrete, of course, we need to write down a matrix and work with it. Yeah? The meetx in GAP lives in the matrix world. There are matrices, there are lists of coefficient vectors or so. There isn't something which takes an object which says, I'm a submodule. So that's why they look that way, and they look a bit spoofy that the names all start with MTX dot. That is a relic of an attempt. 25 years ago, there was a desire to possibly use different implementations of the meetx. And basically, by putting the functions all as components in a record makes it very easy to globally replace which meetx you use. Yeah? In practice, I think very few people do this, but that's why the names look so strange. So, yeah, how do we do this? This is so. These are just an example of a few of such meet-x functions. I take the symmetric group on 6 points just to make an example, and I write down permutation matrices for these generators. For permutation matrix, I need to indicate the degree because in gap permutations don't have a natural degree, just the natural number of points which are moved. Yeah? The permutation 1, 2 in the symmetric group as 6 still needs to get a 6 by 6 matrix, not a 2 by 2 matrix. That's why this degree is given, and I do it over the field with 3 elements. Why that? Just because the example turns out nice. So I get matrices, and yeah, these are written here, are printed like lists of numbers. Yeah, that's how gap represents finite field elements. I can tell you why this happens some other time. I call this G module by mats. That's the list of matrices and the field. Why do I give the field? Because I actually might want to consider it not over the field with 3 elements, but over the field with 9 elements or so. That's why I need to give the field. So I get something which is represented as a record with some components, yeah, dimension, field, the list of matrices. And now I can ask, for example, is it irreducible? And that calls basically Norton's criterion, which I just described to you. It says false, and then I can ask for a submodule by basis, which it gives me. That's what it found constructively by saying the test failed. I can ask, that's where the name meet-x comes from, to run the breadcrumb algorithms, cut apart as long as you can, and we get composition factors. And the composition factors here I'm not showing you all because that is a lot of things matrices print very big. So I'm not showing you the boring bits. I find a module of dimension 1 twice, so 2 isomorphic composition factors of dimension 1 and 1 composition factor of dimension 4. If you know representation theory, you know what is happening there. But we don't need to, this isn't really needed here. I can ask for the basis of all submodules. I have the trivial submodule, the whole submodule, 1 of dimension 1, 1 of dimension 5. This one-dimensional one lies in the 5-dimensional one. That's where the 4 comes from. I can use the induced action on the submodule and the factor module. This basically does the base change so that the matrices have block change and cuts out the blocks. That's the action on the submodule. That's the action on the factor module. That's the action on the whole module in a basis where the matrices have block form. And that is this basis which is chosen, which would tell me how to do the base change. Yeah, and the basis is given as a list of vectors, not as a basis object. There are even things which allow me to calculate module automorphism groups or test isomorphism of modules. The module automorphism group is a group of matrices, of course. Yeah, so that these are things which one can do, for example, with modules. Yeah, and I think, is this all what I wanted? No, sorry, there is a little bit more. How much time do I have?
So you started at 10 past, and
It's 10 past, okay. So since we are close to Geneva, I think I should stop at this point.